So we're continuing to talk about multiple regression, and now we're talking about the predictability. And again, the predictability equation is simply adding on each one of the significant predictors that we have determined we're keeping in our model. So multiple regression can create equations much like simple regression to predict outcomes. Multiple regression can also create better predictions since you have more information to base those predictions on, assuming that each of your predictors is significantly related to your outcome. So again, a simple prediction of graduate school success, y prime, might be your constant plus your B weight, 3.6, and the person's score on GPA. But if we actually had GPA, GRE letters and statement, and all of those were significant, our regression equation, our prediction, would be again an overall constant. What would the person's value be predicted? What would their predicted grad school performance, their Y prime, be if all predictors were at 0? That's constant. Then plus the B weight for our first predictor times their score on that first predictor, the B weight of the second predictor times their score on that predictor, the B weight of their third predictor times their score on that predictor, and finally, in this case, with 4 predictors, their B weight of the fourth predictor and their score on that fourth prediction. And again, we would calculate Y prime the same way we would have calculated it for a simple regression. And again, if we wanted to look at the error between Y prime and actual Y in our original data set, we would do that the same. We would also use the same equations and the same process to actually calculate the standard error of the estimate. And again, if we wanted to create confidence intervals. So let's talk about some of the additional ways that we can use non-continuous variables in a multiple regression. So I've already touched on this with categorical variables. So basically, remember, categorical variables are nominal variables. The numbers do not represent more or less of something, and the numbers do not represent equal distance. So again, if it's a dichotomous variable, generally speaking, values are going to be coded as 1 or 0. 1 present, 0 not present, such as history of alcoholism or no such history, or male versus female. Now, again, because these are arbitrary numbers, sometimes people will actually code these as +1 or -1 to make it a little bit easier to tell which one, if there's a relationship between the dichotomous variable and the outcome, to kind of get an idea of which group actually is related better to that outcome. But again, this is arbitrary. You could just as easily name these 10 and 20, 30 and 10, it doesn't matter, 3 and 7. But again, generally speaking, the reason to get in the habit of 1 and 0 is that if you have any dummy variables, we are going to use 1 and 0 because 0 does need to represent not present. Now, if we have a categorical variable with more than 2 levels, we need to create k-1 dummy variables where k is the number of possible levels. So again, if we had a variable, a categorical variable with 4 levels, 1, 2, 3, and 4, and let's say it's simply representing year in school. That's technically potentially an ordinal variable, but at this point we're just going to treat it as a categorical variable because of the example that I came up with. So again, there's 4 levels, 1, 2, 3, and 4. And again, 4 minus 1 is 3. We're going to need to create 3 dummy variables. So each dummy variable recodes the variable as a present or not present for each possible level. So actually I have a better example here. So we have religion. Levels are Christian, Buddhist, and Hindu. So we have 3 levels. We can't enter that variable into a regression. The numbers are not necessarily ordinal. They're certainly not continuous. We can't necessarily, in fact, they're arbitrary. So whatever relationship we found would be based simply on the order we had assigned the numbers. If we assign Christian 1, Buddhist 2, Hindu 3, we might get a very different result than if we coded Christians 2, Buddhists 1, and Hindus as 3. Since the numbers are arbitrary, the only thing we can look at is the difference between 2 of them. Because at that point, it doesn't matter what the numbers are. We'll still be able to look for a linear relationship that is not impacted by our choice of which numbers were assigned to which categories. Now again, with Christian, Buddhist, and Hindu, we have 3 levels, so 3 minus 1 means 2. So we'd make a dummy variable, a new variable that is Christian or not. So 1 is Christian, 0 means either Buddhist or Hindu. Then we'd create a Buddhist one, where 1 represents Buddhist and 0 represents not. And now what we've got is that if someone is a 1 on the first variable and a 0 on the second variable, we know they're Christian. If they're a 0 on the first variable and a 1 on the Buddhist variable, we know that they're Buddhist. And if they're a 0 on Christian and a 0 on Buddhist, we know they're Hindu. So again, by the very nature of the categorical variables, we don't need to create a dummy code for every potential outcome, just k minus 1. Now, how you actually find the condition of Christian versus Buddhist versus Hindu, the Hindu, of course, is 0 and 0. That means that the condition with Hindu is the intercept. It's what happens when the value you have for those variables are all 0. If you do have an ordinal variable, for example, the idea of year in school, for instance, 1, 2, 3, and 4, 1 being freshman, 2 being sophomore, 3 being junior, 4 being senior, you have to make a call. You can either treat it as a nominal or a continuous variable depending on the range. The greater the range, especially if you check that variable and you have not violated the assumptions of normality with it, I would suggest just leave it as an ordinal variable, do not do a conversion, and enter it as if it was continuous. But again, we're doing this if there's enough levels. In other words, the ordinal variable has multiple outcomes, probably 4 to 5 or more, and it's not violating the assumptions of normality in the data. If it's a smaller range or it violates those assumptions, we probably are going to need to treat it as a nominal categorical variable and create dummy variables. So for example, if we had 3 levels of attractiveness, very unattractive, moderate, very attractive, we might find that those do not necessarily result in normality of data. There might be some skewness. It may not necessarily look like a normal data set, and it violates those assumptions. We find a violation of kurtosis or skewness, or we may find outliers. At that point, we would need to break this up into treat it as a categorical variable, and since it has 3 levels, we need to create 2 dummy variables. So again, we could also look at other various things like rank transformations, larger ratio. The larger the range, the closer the nominal data becomes fairly similar to ratio data. And again, just recognize that it depends on whatever is most useful and most meaningful. So for example, again, if we have class rankings, for example, best in the class, second best in the class, third in the best in the class, one of the questions we can ask in that case is, do we actually have their actual scores? And as those scores potentially on ratio or continuous data, why aren't we using those? If we do have class rankings, and we have a lot of them, so we have a large range, so it'd be fairly cumbersome to break that up into a bunch of dummy codes. For example, let's say you have 32 people in the class, so you have 32 class ratings. You find it's not normally distributed, you're violating the assumptions. Well, 32 means you'd need to make 31 dummy codes. That's excessive. And then not only that, if you only have 32 people in the class, you don't have the power to make that many variables to add to your multiple regression. And that's where we might actually do transformation. So remember, one of the solutions that we can do when we have data that's not normally distributed is we can try a mathematical transformation. We might take it to log 1, for instance. So we could also look at that as a potential answer. For higher order trends, we're talking about nonlinear trends. And again, whenever we're testing a nonlinear trend, we are going to let the linear trend have the first shot at the explained variance in the outcome. In other words, we're going to use a hierarchical technique. We're going to make sure that the linear trends, the variables as they were measured, are the first thing entered. But we then can check above and beyond, is a nonlinear trend a better answer? And we would mainly do this, honestly, if theory suggested it, or if we saw in the scatter plots data that looked as if it was nonlinear. So how we do this is fairly simple. We take the original variable, and for quadratic, one bend, so an upside down U or a right side U, so a single bend in the line of the data, nonlinear, we'd simply multiply the variable by itself. So the way we create that quadratic one bend nonlinear trend is we take the original data and square it, and that would now become our nonlinear term. So we're adding a variable in SPSS. We're also adding a variable to the model that we're doing. For cubic, 2 bends, so again, kind of like a sine wave, we take the predictor to the power of 3. We take each person's score and raise it to the power of 3. 4 bends, power of 4. 5 bends, power of 5, and onward. It's very rare that we find in psychological research anything beyond a cubic trend. And usually it's quadratic, a single bend when we find them. So again, we can also look for interactions. The relationship of one predictor and the outcome depends on the value of another predictor. And again, this is above and beyond the individual predictive power of those 2 predictors. We compute the interaction term simply enough by simply multiplying the 2 predictor variables. So variables can be continuous or categorical, and it's often easier to interpret with a categorical variable. But remember, if we're talking about a categorical variable in multiple regression, we're talking about a dichotomous variable, so two levels. So for example, we might look at drinks per week and smoking marijuana on stress level. So in this particular regression equation, our first predictor is simply how much you drink a week. Our second predictor is simply how much you smoke in a week. But the third predictor is the interaction between drinking and smoking. So as you drink and smoke, is there an additive or a multiplicative effect of doing both of those above and beyond the individual effects of one or the other? And the way we calculate this is, again, we create a new column in SPSS, and we simply multiply everyone's score on drinks by their score on marijuana, or whatever the two variables are that we're looking at. So if the interaction is significant, the first thing we want to ask is, does it actually remove the original initial relationship? So again, we're going to look at that model. For example, when we actually are looking at the entire model, when we add the interaction, does the individual relationships of those two predictors no longer become significant? In other words, do they drop out of the model? If so, we have a true interaction where there is no direct effect. It's all in the interaction. And that's what we were actually originally detecting in those individual effects. More often than not, we're going to find a partial moderation where the individual predictors are still directly predicting above and beyond the interaction, but the interaction significantly adds to the model as well. So if the interaction is significant, we have to define the nature of the interaction. So for example, we know if we find a significant interaction, in this case between X1 and X2, that smoking marijuana moderates the relationship between the number of drinks per week and one's stress level. In this case, though, if it was dichotomous, in other words, if the amount of drinking was the number of drinks per week, a continuous variable, but smoking marijuana was a yes or no question. Do you smoke marijuana or not? In that case, we can simply separate the regression analysis. We can basically look at what is the relationship between, what is the predictive relationship of drinking amongst smokers, marijuana smokers, and what is the relationship in non-smokers. So we would divide our data set into smokers versus non-smokers, and then we'd run a separate regression to look to see how the regression prediction, the regression coefficients, change. And we'd also probably graph this out, and we might find something like this. That in marijuana users, there really isn't an effect of drinking. In other words, the number of drinks really didn't affect stress levels. Drinks are at the bottom, stress levels are along the side. However, in non-marijuana users, drinks had a direct effect, that actually the more you drink, the higher your stress levels. So this would show us the nature of the interaction. We're looking at how the actual prediction lines change with the prediction between drinking and stress based on whether you're a marijuana user or not. And the reason we're looking for this again is that we found a significant interaction. Now, if both predictors are continuous, you're going to have to make some choices. So again, our second predictor moderates the relationship between our first predictor and the outcome. So in this case, instead of you smoke or not, we have the number of joints smoked per week versus the number of drinks per week. What we generally want to do here is we just want to select one or two specific variables for that predictor, that X2. So for example, we might decide, let's take a look at when people smoke 4 joints a week versus when they smoke 8 joints a week, and then look for the relationships between those two. The values we select are usually going to be approximately 1 standard deviation above the mean and 1 standard deviation below the mean. And again, we're going to separate our data set and take a look at what those relationships look like at basically high levels of marijuana smoking versus low levels of marijuana smoking. So each additional variable should add to the model. And again, as we are actually looking through whatever model we're doing, one of the questions we're asking is, as we add additional variables, are they significant? And do they actually add to the overall significance or overall predictivity of the model? Other existing variables retain significance as well. So as we add them, are we also retaining the original significance? So the way we measure this is a measure of model fit. It's an omnibus test. It doesn't tell us which predictors are significant. It simply asks, if this particular group of predictors, is it significantly predicting the outcome? And then it allows us to compare model to model. So for instance, if we're doing a hierarchical regression, we're going to have block 1 model, block 2 model, and maybe even block 3 model. So not only are we asking, is each model significant? We then are asking within each model, which predictors are significant. And then we want to ask, as we add predictors, are we not only finding significant prediction, are we getting an overall better fit to the data? So each model is going to have an R square and an F. R square is going to be the total variance in the outcome that is being explained, basically effect size of our multiple predictors, and F is whether that model is significant. But we're also, as we move past the first model, we're going to get an R squared change. In other words, does the model get better and how much better with each addition? And an F change. Is that increase in prediction significant? Now, within the final model, once we've decided what model we're going to use, which predictors we're using, that's when we're going to look for significant t-tests of each predictor to make sure those predictors are still significant as well. And also, as you're going through this project, or this process of looking at different models, if you notice, for instance, that one predictor is kind of fading in and out of significance, in some models it's a big predictor, in some models it's not a predictor at all, that's another clue you've got multiclinearity. So if you see, the coefficients will change from model to model, but they should be relatively small changes as you move things in and out. If you find large ones happening back and forth, that's another indication you probably have a couple of predictors that are highly correlated.